You know, every single time you send an email, watch a video, or just scroll through your feed, you're using the internet's universal postal service. It's called IP addressing, and it's the invisible system that makes sure every little packet of data finds its way home. But this system, designed decades ago, presents a really fascinating puzzle in our modern hyper-connected world. So here's the big question. With literally billions of devices online right now, your phone, your laptop, your smart fridge, how on earth has this old system not completely run out of addresses? I mean, it should have happened years ago, right? Well, that is the mystery we are going to solve today. We're going to uncover the clever engineering that keeps the whole thing running.
All right, so the foundation of all of this is the IPv4 address. At its core, it's just a 32-bit number, but we usually see it as 4 numbers separated by dots. The best way to think of it is as a unique digital home address. Every single device needs one to send and receive data, making sure your information gets delivered to the right digital doorstep and not your neighbor's.
Now, in the very early days of the internet, engineers needed a simple way to manage all these new addresses. Their first solution was something called Classful Addressing. Basically, they sorted the entire address space into just a few big, predefined categories. Think of it like a filing cabinet with only a few very large drawers.
And here is where the problems started. Just look at the insane jump in scale here. You had Class A, which gave a single organization over 16 million addresses. Then Class B, with about 65,000. And finally, Class C, with just 254. So your choices were basically giant, large, or tiny. There was absolutely nothing in between.
And that complete lack of flexibility created a massive problem. The system was just incredibly, unbelievably wasteful. And as the internet started to explode in popularity, this waste wasn't just some minor inconvenience. It was a full-blown crisis that was threatening to stop the internet's growth dead in its tracks.
It created what you could call the Goldilocks problem, right? So imagine you're in university and you need about, say, 1,000 IP addresses. Well, a Class C block is way too small, so you had no choice but to get a Class B block. But that gives you over 65,000 addresses, meaning you'd be sitting on and wasting more than 64,000 of them. Neither option was just right, and millions of perfectly good addresses were getting locked away, totally unused.
So to fix this incredible waste, engineers came up with a really ingenious solution called subnetting. This was the first major innovation that basically saved the internet from its own rigid design, and it finally allowed network admins to create custom-sized address blocks.
The idea behind subnetting is actually pretty simple. You take one of those huge, wasteful blocks of addresses, like that Class B network we just talked about, and you chop it up into smaller, much more manageable subnetworks. It's kind of like taking a giant plot of land and suddenly being given the tools to fence off smaller, custom-sized lots for exactly what you need. So, how does this work? Well, the magic is all in how we look at that 32-bit address. Engineers figured out they could borrow some of the bits that were originally just for identifying individual devices or hosts and repurpose them. They used them to create a brand new identifier for these smaller subnets. This gave us a much more useful 3-level system: network, subnet, and host.
Okay, so that's the what. But how does a router out on the internet actually figure out which specific subnet a device belongs to? Well, it does it with a surprisingly simple calculation. Let's walk through a real example to see exactly how it's done.
To find the right subnet, a router uses 2 key things. First, something called a subnet mask, which is basically a template. It tells the router which part of the IP address is the network and which part is the device. And second, it uses a logical operation called a bitwise AND, which is just a fancy term for a really simple way of comparing the IP address to that template.
Okay, so here's our mission. We've got a device with this specific IP address and this subnet mask. Our job is to use these 2 pieces of information to pinpoint the device's exact subnet ID. All right, let's break this down. We really only need to pay attention to the last number in each address, since the mask is maxed out for the first 3. First, we convert the IPs 117 and the masks 224 into binary. Then, we do that bitwise AND operation. And don't worry, it sounds complicated, but it's not. Think of it like a filter. A 1 only gets through to the result if there's a 1 in the same position in both of the numbers above it. This one simple trick instantly strips away the device-specific part of the address, leaving us with just the sub.
After we run that binary through our AND filter, this is the number we're left with. And converting that back into a regular decimal number gives us our answer: 96. And there you have it. The subnet ID for this device is 203.112.111.96. And this is exactly how any router on the internet can do a split-second calculation to find the precise subnetwork for any IP address that comes its way.
Now, subnetting was a fantastic fix. It was brilliant. It bought the internet years of extra time. But at the end of the day, it was still a patch on a fundamentally broken system. To truly scale to what it is today, the internet needed to break free from those old A, B, and C classes once and for all. And that brings us to the modern system.
This is CIDR, which stands for Classless Interdomain Routing, and it does exactly what its name suggests. It completely throws out the old class system. Instead of having just a few fixed block sizes, CIDR lets you create networks of almost any size you want, just by using a slash and a number to define the network's boundary. Now, for this super flexible system to work without just creating total chaos, it follows a few simple but really clever mathematical rules. The addresses have to be in one continuous block, the size of that block has to be a power of 2, and the very first address has to be perfectly divisible by the size of the block. These rules are the secret sauce that lets internet routers handle traffic with blinding speed and efficiency.
So you see, this whole journey from that rigid, wasteful, classful system to the clever patch of subnetting all the way to the modern flexibility of CIDR, this is the story of how the internet was able to grow from a tiny academic project into the global network that we all depend on for, well, pretty much everything today.
Oh, and there's one last clever trick that helps us conserve addresses: private IPs. Your Wi-Fi router at home? It uses addresses from one of these special reserved ranges. Since these addresses never ever show up on the public internet, millions of homes and offices can all reuse the exact same addresses internally, which saves a massive number of public ones.
And this quote really sums it all up, doesn't it? As one of our sources puts it, the original system simply did not foster the efficient allocation of a finite address space. So really, the entire history of IPv4 has been one long masterclass in creative problem solving, all to overcome that one fundamental flaw.
Through all of this incredible innovation, the old 32-bit IPv4 system has managed to survive way longer than anyone thought possible. But now, with the Internet of Things bringing potentially trillions of new devices online, the big question remains: have we finally reached the absolute limit of this system? And what comes next?